Good afternoon, everyone, and especially for the participants from Zoom. Welcome for our session, and this is a public event we organized by the Work Package 5, Artificial Intelligence. So this subject is about the Einstein Telescope project, and we're going towards the end of the 2-year program. So the whole theme of our workstream is to identify what are the useful information and we can extract from gravitational waves and what kind of AI method we have applied for that. And again, welcome all you for this event, and I'm very happy to introduce for today's agenda. Okay, so today we have multiple speakers for our events. First, we will be inviting Stefan Hilt. He's the professor from Maastricht University. He will give us a little bit the background, why we do this project and why it's very relevant and interesting for us. And then second is our team presentation, which we would like to outline what we have achieved so far, and that will be delivered by Tom and Andrew. And the last, I will give a little bit outline of what we do as a company in combination of the research institution and why we found this so interesting for us. And any questions you can ask in the meantime, and if you have any other things, you can also leave on the message and we can reply later. Then I would give the floor to Professor Stefan Hilt and welcome for his speech.
Yeah. Okay, good afternoon. My pleasure to be here. I was asked to talk a little bit about the Einstein Telescope and kind of what are the challenges for data analysis in there, which relates to this work package in here. And I will give you on the way a little bit of an overview of the Einstein Telescope. So we have come a very, very long way from Albert Einstein as a consequence out of the theory of general relativity to predict gravitational waves. Yeah, that's more than 100 years ago that he did this, was actually in 1915 or 1916, depends on how you look at the publication. And it took our field about 50 years until people started to think about, oh yeah, how can we actually measure these gravitational waves? And then it took another 50 years to develop the technical capability to build gravitational wave detectors as we know them today. And you see here on the right-hand side, the observatories, 2 in the US, 1 in Pisa, and 1 in Japan, which, you know, have an incredible sensitivity to measure these gravitational waves. Gravitational waves are ripples in space-time, and more or less what you need to do is you need to do an incredibly accurate length measurement, and that's what these interferometers do here, where you see you have these kind of perpendicular arms and you measure how long does it take the laser light to go from one end of such a tube to the other end and compare it to a tube which is perpendicular. And out of the difference, you can see whether there has been a gravitational wave or not. This is a field which really started off only a few years ago, where the first discovery of gravitational waves happened in 2015, was published in 2016. So that was the first time people were actually listening to the sound of the universe, a completely different way to look at the universe. So far, everything in astronomy was about electromagnetic observations, so obviously all different kind of flavors, yeah, optical light, but then radio waves on the one end, X-rays and gamma rays on the other end. But since then, and this is what is shown here on the left-hand side, we have observed quite a few gravitational wave signals. By now, it's about 100 of these. And they have allowed us to learn many different things about the universe, which you know, we have not seen before. Yeah, every time you switch on a new way of looking at the universe, you find something new. And maybe to explain it a bit, what you see here on the left, on the right-hand side, to give you an example, these are all systems that we know eject gravitational waves, black holes, neutron stars, and so on. And what you see here is on the left-hand side is the mass of these systems. Our sun is a very, very light such system. Yeah, I would go at 1. And then you have here black holes. And these black holes, the purple ones here, are the ones that we have observed beforehand, before the existence of gravitational waves, just by standard astronomy. And the nice thing now is what you see here is they cluster around 5 to 10 solar masses. While if you now look at the ones we observe with gravitational waves, which are these blue ones here, you see they cluster at a completely different mass. If you wouldn't have had the gravitational waves, you would think, oh yeah, the population is given by these lightweight black holes. But we now know that this is just the tail of the distribution that we have seen. And actually, most of the black holes we observe have a completely different mass range. And that was one of these nice things. You switch on something new, you learn something new, and you have to go and, back to the blackboard and revise your series. So now we are kind of, observing these on a regular basis. I don't want to go too much into detail of these plots here, but just to show you now that you have about 100 events, you can start to look at the properties of these populations. Yeah, whether these black holes spin, whether if 2 black holes merge together, whether one is big, one is small, all of these kind of different source parameters, which tell you obviously something about the way how they were formed, what was the environment of these objects, where they formed billions of years ago, and so on. So this is now really kind of starting, and we're just at the brink of this. As I said, discovery was just a few years ago. So now we are slowly learning how to do astronomy with these objects. And we have learned quite a few things. I think it's a bit too much for the few minutes I have to go in there. So this is a current state. We have these gravitational wave observatories, these discovery machines, LIGO and Virgo. And now, the topic of this webinar is the Einstein Telescope. So you wonder, why do we need the Einstein Telescope now? And the key thing is there that if you think about it at the moment, yes, we can hear gravitational waves, but only very faint. We only get very, very loud signals only for a very short moment. Maybe to make a comparison here, we see about 1 gravitational wave event per week, and it takes about, as long as it takes me to snip my fingers, a fraction of a second, which means that in a week we have this once snip, and then we have 6 days, 23 hours, 59 minutes, 59 seconds noise. Okay, so that's the current situation state of the art. The Einstein Telescope will actually turn this around. Now that we know gravitational waves are there and how much we can learn from them, we really want to go all for it and build an observatory which allows us to more or less listen to the whole universe with gravitational waves. And the amazing thing there is really that instead of listening all the time to noise, we will see about 1 million signals per year. So many, 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 many. But also we will listen to the signals for much longer time. We will not just hear the last few seconds or milliseconds before a merger, but for some of these signals, we see them for a whole day. So we turn the challenge completely around. Before you had to find the signal, like the needle in the haystack, you had to find the signal in the noise. And now actually, in the Einstein Telescope, you will have so many signals in there that the challenge is how to disentangle all of these signals. So that is what we really want to do. And for that, oops, let me skip over that. So why do we want to do this? The key thing is we really want to learn about the universe, and the science is fantastic. We are now coming to the point, we have taken the first image with electromagnetic waves, the shadow of a black hole. We are now starting to see and probe general relativity with black holes, and starting really to see maybe the first effects of what happens with space-time at the event horizon of a black hole, which might tell us a little bit about quantum gravity, how gravity actually fits together with the rest of the forces in our universe. So there's many, many different science cases for the Einstein Telescope. I just mentioned a few to understand how the universe is actually expanding, where it's coming from, where we are going to. But also we have unprecedented capability to look back in time, and with the Einstein Telescope, we will be able to look much, much further out into the cosmos, which means much, much further back in time, and really go back to the time before the first stars and the first galaxies were actually formed, to see what is out there. And this is something you can't do with classical astronomy. Good. There's many more sources that we are interested in: black, dark matter, dark energy, many other sources that I haven't talked about: neutron stars, supernova, and so on. So quite a lot of different things. And obviously, the most fascinating for me is always, when you switch on something new, how nice would it be, not only to find the things which are out there, but to find something which you have not thought about that might be there. Good. Now, coming back from the Einstein Telescope, what are the challenges if we talk about computing, data analysis? And this is really kind of, how to find low signal-to-noise signals in, very short signals in a noisy data stream. Once you have found a signal, the next question is, how significant is what I found? Is that just an accident? Just some Gaussian noise overlapping, which by chance gives you a signal, or is this a real signal? And then once you have convinced yourself this is really a signal from a cosmological source, you really want to say, okay, you don't stop there saying, oh, I have seen something, but then you want to really dig down and understand, oh, is this a neutron star? Is it a black hole? What are the properties? Do these sources have spin? How have they come together? How have they evolved over time? So these are the data analysis challenges we have right now. But as I said, if we want to scale this up to the Einstein Telescope, then our current challenges or techniques might not even be able to be scaled up. And here I put a slide just to show a few points why this is the case. We have to go to much lower frequencies. One of the big capability of the Einstein Telescope to see so much further out in the universe is because we are managing a sensitivity curve which allows us to be sensitive at much lower frequencies, much lower tones, which allows us to see further out. That comes with a huge computational cost because now all of your signal templates need to be much larger and so on. And at the moment, we wouldn't know how to run these even on the biggest clusters. In addition, there are many more objects out here, tens of thousands, hundreds of thousands to millions sources out there. And in addition, you also want to be able to do sky localization, early warning now that your signals are not in your detector band for a second, but for a much longer time. You might actually be able to predict where the final merger will happen. And that we have seen earlier from a neutron star merger has spectacular science where you can actually see elements being formed and do lots of interesting tests out there. Finally, the last challenge, and then I have posed enough challenge, I hope, is how to deal with these overlapping signals. I show you here a data trace on the on the right-hand side, where at each of these kind of big spikes, you have one signal in there, but you see many of these mergers are actually overlapping and you might have long mergers underneath there. And to disentangle these, that is something that needs quite some effort. And so far, we haven't really found the solution. And that's why we are so happy, like in this work package here of this project, people working on these challenges. Good. I realized this was quite a fast run through of Einstein Telescope, but I hope it was something for everyone, for the people who didn't know anything about gravitational waves, but also for people in the audience who know about gravitational waves and are really interested in, what are the challenges in data analysis. And here, thank you very much for your attention and open for questions.
Are there any questions online? Any people want to ask? Not, I assume. Yeah, then thank you very much for your presentation, and we move to the next one. And this will be given by Tom, and his topics about the conditional gun.
Good afternoon, everybody. My name is Tom Dooney. I'm a PhD student at the Open University, and today I'm going to be giving a presentation titled CDVGAN2, a flexible model for generating gravitational waves data. So I'll first start off with an introductory video that was actually made by our media department in the OU.
Gravitational wave detectors measure tiny space-time disturbances caused by cosmic events. These waves carry valuable information about their origins. However, the highly sensitive detectors also pick up glitches, transient noise signals that hinder gravitational wave analysis. Glitches can mimic true astrophysical signals, posing challenges for astronomers. Scientists use advanced techniques like data filtering, noise modeling, and signal simulation to identify and mitigate glitches. Machine learning algorithms called GANs can learn realistic glitch patterns and generate synthetic glitch signals efficiently. These synthetic signals enhance anomaly detection and glitch characterization algorithms. The introduction of next-gen detectors like the Einstein Telescope is expected to increase the detection rate of glitches and astrophysical signals significantly. These approaches currently under development within the Einstein Telescope Technology project will enable scientists to effectively discriminate glitches from astrophysical signals, thus enhancing their ability to analyze and interpret new discoveries.
So in this presentation, I'm going to be just going into a little bit more detail about the inner workings of GANs and how we can use them to our advantage. So in essence, this is pretty much the process of detecting gravitational waves. Some source like two colliding neutron stars or black holes, they merge together, and then these are picked up as a signal in our gravitational wave observatories here on Earth. And you can see on the right-hand side, this light blue gravitational wave signal deeply embedded in detector background, which is shown in dark blue. So Stefan talked a little bit about the really high sensitivities involved. So these detectors, the current generation, detect length differences less than 1,000th of a proton. So really sensitive instruments. And as a result of that, they pick up these noise artifacts called glitches. And the problem with glitches is that they can look very like gravitational wave signals that we care about, and they can trip up our data analysis pipelines and start triggering our trigger systems and cause problems in general for data analysis. So we want to be able to identify where signals occur in noise, whether they're glitches or gravitational waves. We want to be able to feed some sample with our background noise plus potentially a signal inside that. We want our detection model to tell us if we actually indeed have a signal in there. So I show this signal embedded in noise in orange for clarity. So we'd hope that this detection model will spit out a 1 if we have some sort of signal inside it. And if we don't, if it's just background noise, just inherent to the detector based on the sensitivity, we hope that this detection model will spit out a 0. And this is like some loose idea of some first step at identifying a signal in noise. And this will become later when I talk about how we can use GAN generated data. So simulating gravitational waves and also glitch signals with machine learning can offer many benefits. We can learn the underlying distributions of different signal classes, potentially bypass expensive simulations, particularly for use for gravitational waves data. They can be very expensive to simulate outside of machine learning. We can also use synthetic data to augment data sets to improve accuracy of detection models like I just showed. We can also use synthetic data to validate detection schemes to make sure that they're working correctly. To simulate this synthetic data, I use what's known as a generative adversarial network. So we can see on the right-hand side some images that everyone's probably familiar with, and you can condition these GANs on different types of emotions. So you can see here that the GAN's able to output some realistic looking image of some famous face, but based on some emotion that the user actually provides to the model. So I want to use conditional GANs, but instead of conditioning on different emotions, I want to condition on different types of signal that we care about in these gravitational wave detectors. And you can condition on different types of gravitational waves, different types of glitches. And how this GAN works, which I've developed, it basically uses derivative signals as a form of just controlling the learning of this model. So you can see a glitch signal. It's called a blip glitch on the bottom, just on the left, and its corresponding derivative signal on the right. So these GANs use these derivatives to help guide their learning. So I'll just give a little bit more detail on how this novel GAN method differs from just a traditional normal GAN. So GANs work by basically two competing model components known as a generator and a discriminator. So the discriminator's job is to try and learn what is a fake signal and what is a real signal. And a fake signal actually coming from this generator model component. So the generator just starts off learning some, you can see on the bottom right, it first just learns some noisy signal shape, which it thinks looks like a glitch. And then the discriminator starts slowly over the training epochs to realize that there's more diversity in this data set. And you can see that now on the bottom right. And this encourages the generator slowly, little by little, encourages the generator to generate more realistic samples. And so these are known as adversaries, this generator and discriminator. And some motivation on looking at using derivatives for this type of learning is that I often found that when you implement these GANs on signals, that you can get this high frequency contribution. Hopefully you can see my mouse, maybe not. Yes, on the left-hand side image here. And on the right-hand side, you can see that these have been minimized slightly. And after noticing that earlier, I thought this would be interesting to look at. So CDVGAN makes a very simple addition to this original 2-player game. It just adds in an additional player, a second discriminator, and this just looks at the derivative signals. I will also be presenting CDVGAN 2, which makes yet again another simple addition, and it just adds on a third discriminator that looks at the second order derivatives, so the derivatives of the derivative. So we train these GANs on different signal classes. One thing I forgot to mention is the whole idea of conditioning here. So you see these C notation here and here. This is basically us telling each of these model components what signal we're feeding it at any given time. So you can use in my case, I use 3 different signal classes. 2 are glitch classes that we see in the detector, 2 different types of glitches. And then the third class is some simulated binary black hole events. So these represent signals that might come from 2 colliding black holes. And we feed these different classes of signal to train the GAN. And we tell the GAN each time we give it a certain type of signal, what class it actually is. So after you train it, like the way we saw in the GIF in the previous slide, you can then on the output give the GAN a specific signal class. For example, you can feed it some vector with like a 1, 0, 0. And you can see on the top row here, when a 1's in that first position, it corresponds to a blip glitch. When it's in the second position, the other glitch class we have, the Tomty glitch. In the third position, a binary black hole signal. So this is all GAN generated data. And this has full user control. So they're very flexible, and the user can decide what signal class to generate and how many signals they want to generate. And the GANs can do this very efficiently. They can generate hundreds of thousands of signals in a matter of seconds. So we can do other cool things other than just generating these vertex classes, as I call them, just the standard 3 signal classes. We can sample these class spaces. I showed them above each image. You can look at these as different proportions. So we can see we have a 35% of a blip glitch. You can look at it like that, 5% of the second glitch class Tomty, and 60% of a binary black hole class. So these signals feature that different features from different signal classes in the one signal. And this type of sampling where we basically add up these vectors to 1 and have some sort of proportion type idea, that I call that the simplex data set. And then we can also sample in another way called the uniform data set, in which each of these numbers can be sampled between 0 and 1. So it's just another way of getting these hybrid signals. And then you can do other cool things like interpolate between different signal classes. So in this case, I keep the GAN input constant. So I'm changing the class input here. You can see at the very top of each of these images. But otherwise, I'm keeping the actual input to the generator constant. And in this case, you can slowly go from a blip into a black hole signal, binary black hole signal, into a Tomty glitch signal, back into our original blip signal. And you can see that we wind up at the same signal that we started off with. So we can do different analysis to investigate this synthetic data from the GAN. What's the point of all this? So we would ideally like our standard signal classes that come out of the GAN to be similar to the synthetic data. And to try and see this, we use what's known as principal component analysis. And this basically just compresses these signals into a small compressed space. And we can look at how these different patterns look when we color them by real and fake data. So you can see in the first plot that the fake data matches the real data reasonably well. We can also color by the different classes that we have. So I show different shapes for real and fake, but that's not really important here. What's interesting to look at is I also show these hybrid data sets, the simplex and uniform data sets here as X's. And you can see that these hybrid signals span the space in between these signal classes, whereas the original signal classes, you can see them that they're quite separable in 3 different clusters. So it's intuitive, and it's interesting that these signal classes span the space in between these different clusters for the different signal types. So Just as an application, I showed that you can use this GAN-generated data to actually train these detection models, which I showed earlier, just setting up a simple experiment where we want to try and identify where these orange signals appear in noise, or where it's just a noise-only sample where we just have a Gaussian noise with no embedded signal. And to understand the effect of actually using different GAN models and different model components, like the way I've described, to understand, is it useful to use these derivative discriminators, and how good is the data on the output? We use ablation studies. And ablation studies in machine learning just basically means selectively turning on and off a model component to see its effect on the output. So I'm just showing a table full of different, it's just an accuracy metric here using AUC. It's not very important. Higher number is better. But I just want to draw your attention to the first 3 columns here. So we are pretty much looking at the same 3 models here, just with the addition of derivative discriminators. Otherwise, they're the exact same. So this is the vanilla version in the middle. CDV-GAN adds on 1 derivative discriminator. We can see an improvement in this uniform, the uniform data set when we train that detection model. And then we add on yet another discriminator, we can see an improvement across the board. So using these derivative discriminators seems to have a positive effect on the generated data in terms of training a detection model to find real signals in noise. These last 2 models, it's basically doing the same thing, just using a different architecture. So these 3 models belong to one family, and this belongs to another family here. So this McDV-GAN just adds on a derivative discriminator under a different architecture. Otherwise, they're the exact same model. And we can also see some improvements in 2 of these data sets, which is promising. So some conclusions. GANs can be useful for learning underlying distributions of signals. You can augment data sets, as we've seen, to actually train detection models to detect real signals within noise. We can use the synthetic data for other things, like making sure the detection schemes that we have work and constructing mock data challenges. Conditional GANs, as we saw, we can actually explore the variation within a signal class and also between signal class. So interclass and intraclass variation can be explored, and we can generate data outside our limited training data distribution, which is another interesting thing we can do. We saw that derivative discriminators can have a positive effect on improving the features across multiple GAN architectures. And it can be seen in this context of a signal search. It improves the signal to noise ratio in this case. And another interesting finding, as we saw here, is that a lot of these hybrid data sets do a lot better than this standard vertex 3-class data set. And that's another interesting finding. So they can be useful, these hybrid signals, for searching for multimodal distributions in detector background. So I hope I didn't lose anybody there. Here's some acknowledgements, and should be some partners there. But otherwise, I'm very happy to take any questions if anyone has them. And I thank you for your attention.
Great, thanks. And I have a question. So for all the data that you generate, that's the synthetic data, basically. Is that also can be used by someone else who is really research on that area, or it would be a or the model?
So GANs are very flexible. If they're time series signals like this, you could apply this type of idea to any time series signal that you want. The caveat for using these derivative signals is that they have to be continuous, or at least represent some sort of continuous waveform for it to actually make sense. But you can use this type of idea on any signal class that you could differentiate.
Any other question from you guys? No? Yeah, I think it's great work. I mean, I've seen the progress, and I think there are more already done in the last few months. Yeah, thank you a lot. We have our next speaker. Unfortunately, he's not here, but he is sending a record over. And that is another summary of the work which is done by the University of Utrecht.
Okay. Hello. Thank you for coming to listen to my talk. Let me just make this full screen. And okay. Yeah, so thank you very much. My name is Andrew. I'm currently a postdoc at Maastricht University, and sorry I can't be there in person or even to present remotely, but I'm going to talk to you about some of the updates of the deliverables of our work package, which is about the AI, using AI for the detection of gravitational waves. And this work is essentially on behalf of mostly PhD students and master's students. So Melissa Lopez and Stefano Schmidt, as well as Paloma La Huerta and Robin. And so yeah, I'm just talking on behalf of them. So now let me just jump into this and just remind everyone what is this work package about and the context for it. So the idea behind this work package is to develop artificial intelligence tools that will be useful for detection of essentially non-standard gravitational wave signals, as well as anomalies, some kind of anomaly. And these things are quite loosely defined. And so the idea is that we want to be agnostic to the kinds of gravitational wave sources that we could potentially see in current generation detectors like advanced LIGO and Virgo, but as well as in future detectors like Einstein Telescope. And so that is kind of the main idea, but when we are also sensitive to these kinds of non-standard, non-modeled gravitational wave signals, this also means that we are sensitive to unmodeled noise disturbances, which can hinder the detection prospects of these astrophysical unmodeled gravitational wave signals. And so a big portion of this work package has been developing ways of identifying these essentially these noise disturbances that we call glitches, and distinguishing them in some sense from astrophysical signals. So now I'll jump into essentially the three major things that are the outputs of this work package. One is the ability to simulate noise transients, so these glitches, with machine learning. This is work that's been primarily done by Melissa Lopez, and Stefano Schmidt and Vincent Buda. And the second aspect of this work package has been to detect anomalies present among LIGO's glitch population using another type of machine learning, autoencoders. And this work has been done by Paloma and Robin, as well as with Melissa Lopez and many others. And then finally, Stefano has led work about detecting gravitational waves through features. So essentially through some statistics that you can combine in a certain way to enable detection of true astrophysical signals. So I'll jump into each of these three subjects in the next few slides. So the first is about simulating transient noise bursts. And so in order to do this, a publicly available package called Gangly was developed primarily by Melissa Lopez, who you can see a picture of here. And the idea behind this is to use a type of neural network called generative adversarial networks to learn the underlying features of LIGO and Virgo glitches, and thus be able to use those features to create new types of glitches, or new glitches with different parameters than what were already observed with LIGO and Virgo. And the motivation of this is that at the moment, or at least until this study was performed, there was no way of actually simulating these kinds of noise disturbances. Essentially, people have to rely on a particular method to identify in the data where there are noise disturbances, like these glitches, in order to study them. So with the advent of this work, we are now able to simulate new disturbances, and as well as inject them into mock data, so mock future data like Einstein Telescope. And so the motivation behind this is that the gravitational wave detectors currently and in the future essentially have all of these weird noise disturbances, and when we think about doing analyses with future detectors, we do not know what they're going to look like, but we can kind of guess that it will be similar to what we have already observed. So with this package, we are able to inject these glitches, these fake glitches, into future mock Einstein Telescope data as a way of making the data, the mock data, seem more realistic. And here you have an example of the left-hand side pitch, what glitch looks like. And you have a picture on the right of what a astrophysical signal looks like. And so you can see that quite similar. So this is a major motivation, again, for this work, in that you have to be able to detect noise disturbances and glitches separately. And here's a Python package that was developed to actually do this kind of glitch in them. Now moving on. So the second aspect of this work package was the detection of anomalies amongst LIGO's population of glitches with autoencoders. So the idea behind this work, in contrast to the other one, is that this is an unsupervised approach where you allow the data to speak for itself and to essentially classify itself into the different create different populations itself. And so, whereas in the previous work we used glitches that are known, or that we in order to simulate new ones, in this work we classify the glitches into different categories in a model agnostic way, using a statistic that's called the fractal dimension, which essentially encapsulates the noise disturbances into essentially a second long time series into essentially a single number. And so here you see an example of what the data that we use in this autoencoder looks like. Essentially on one axis here you have all these different auxiliary channels, which are essentially the monitors for different subsystems in the detector. And each of these subsystems could couple in some way that we do not understand to the astrophysical channel that we care about. And so this fractal dimensioning encodes the deviation of the data in this channel from being undisturbed. And so the idea also, in similarly to the previous work, is to compress this data into some embedded space and then regenerate the data exactly as it was before. And when we do this, essentially what you find is that that the data itself clusters into different populations and different categories that allow for the identification of new glitch populations that you wouldn't be able to see in the previous approach, because the previous approach was supervised learning. This work was primarily done by Robin and Paloma with oversight by Melissa. So now, this then finally, I'll talk about feature anomaly detection for gravitational waves. This work has been led by Stefano Schmidt. And again, the motivation behind this work is that some sources of gravitational waves we can model, others we cannot. But in order to detect these sources in some model independent way, we could potentially use particular features of the data and combine them in a certain way in order to enable this kind of detection. And so what is a feature in this case is some change in the time series data here, as you can, that's illustrated here. And so these features can be quantified in terms of some statistics, which are essentially given as time series here. And the actual statistics themselves are not important for the purpose of this talk, but they can essentially take the meaning of like a maximum or a mean or a deviation from Gaussian noise or a variance, something like that, or false alarm probability. And so the combination of these statistics can help us detect glitches or astrophysical sources, as well as to distinguish them. So with that, I just wanted to mention some future activities beyond ETT that we plan to work on, is also to be able to generate glitches from different populations, to quantify the impact of each of these features that I talked about in the previous slide, to detect anomalies with this feature detection algorithm, and also to determine the origin of glitches, which auxiliary channel do these glitches actually come from. And with that, I'm happy to conclude. Sorry I can't be there in person today, but I hope that the people who are there can answer any questions that you might have. Thank you very much for listening.
Okay, that's the presentation from Andrew and gave basically an overview of the University of Utrecht, what has been done on the AI package. That comes to the last presentation, which is our role, so boosting alpha, what we played in the Einstein Telescope project. So why gravitational wave analysis would make sense for financial trading? So there are a lot of common features. So I gave a list of it. For instance, there are multiple data sources to represent the same event. That's what's happening for the current telescope, like LIGOs. They have two different tubes that basically extract the data, while it represents probably the same event happening in the space. And in the financial trading, we have a similar story, like when assets can be traded in the multiple markets, which reflected slightly the price differences. And that's the kind of thing we want to see what techniques can be applied to trade the multiple source data. Second is we actually search something unknown. So we still have a lot of empty spots in the knowledge area that we don't know what's happening in the space. And the same for the financial trading. Actually, it's a very random number and the prices, if you look at the data samples. So actually, we try to understand what is the information underlying and what can be useful for us to use. And of course, there are also a couple of other things. For all the data, in general, in the data analytics world, you have noises, and there are noises can be represented by different reason or causes, and we want to recognize and modeling the noises alone. And the last two things is it's a time series data, and we really like to apply the AI methods in this type of application, because at the beginning, most of the AIs are on face recognition or image recognition, but also later on, to deal with time series data is always a challenge. So given the common features, so the method we explored during the ETT project may prove applicable for both domains. So that's a great example how physics research and can nourish and valorize the other business like us. Yeah, a little bit our approach and what we have done together with our research partners. So if you look at the data sources, we have our own data source, and the gravitational wave analytics also use their own data. However, the data shares the similarity, as I said before. There are the real signals, and which something we want to understand. And there are also noises, and the noises can be classified into two different types. One is the glitches and one is the Gasson noise. That's a kind of like very random background noises. So we took two different approaches. One is on the conditional gone and the probabilistic models and all the other things, which is focused still on glitches. So those are the noises. And what we are trying to do is also to use different AI model, but more try to understand the useful information hidden in the data samples. And that is coming from a very traditional CNN models to the explainable AI pattern. That's something we really spend a lot of time on and which is very interesting to see. So basically, it's a new approach. I think we also did our research and not widely, let's say, applicable cases that we have been identified in our area. And so the explainable AI pattern, basically, we're trying to matching with the Japanese candlestick. This is a very common, let's say, the image or the information representing the trading informations. And we use the triple barrier labeling to use the AI model. We try to identify which are the strong buying signals by looking at the pattern, which is simulating the human being reading the charts. And when there are very strong learnings to give the results that it's a strong buy signal, then we perform that task when we see this similar patterns happening again. So the same concept have been applied for buy and sell both sides. And so that results in a kind of experiments already in the testing phase. We basically take the IX, so that's Amsterdam Exchange index from 2010 to 2020 as a data input. So the green line basically shows if you invest, let's say 100 euros at 2010 at the beginning, and after 10 years, you're able to reach a return around 170, 180 euros. So given the 10 years, your assets will grow 70% just by doing nothing and buying the index. So that's a basket of all the performance, all the stocks performance within the last 10 years. However, the active trading goal is try to utilize the information and try to outperform the index. So we used our model for the last 10 years. We basically achieved a higher return. So that's around 200%. That is higher than the index, which is quite difficult. However, we see there are a lot of shortcomings of that model. For instance, there's a huge drawdowns we see. So which means if you invest in 2015-16, and if you want to cash out your portfolio, you may suffer a big loss. And that kind of risk area is the thing in the real life we try to prevent, because on paper, you see, okay, it's just running a simulation and you see the performance. However, in the live trading, you need to look at a lot more aspects to that. So this is basically a short story of our work and our engagements. If you have any questions, please ask. I would like to check a bit the online audience, if there anybody having a question.
Sure.
Huh?
I do have a question.
Oh, okay.
Yes. Last example, go back to the slide.
Yeah.
What does your model do exactly more than the benchmark? Because it's the drawdowns and the upsides here are much larger than the standard deviation of the benchmark. So what does the model add to that in order to be able to return that?
I think this usually is a method is called passive investments, which means you does nothing. For instance, you buy a basket of everything which is in the IX, and you just let it wait, and then that's the benchmark we talk about. And what we're trying to do is, of course, we look at if there's an opportunity to buy, we buy, and if there's a potential or chances to lose, then we sell that assets, and then we trade them more actively.
Just a much more active strategy.
Yeah. So it's active trading. And then by doing that, first of all, you have cost in trading. So there are the money which you paid for exchange, which taking out from your return, that's one. And if you trade more, it costs more money, and it probably not necessarily you gain that money and you're still losing on your prices. That's one. And the second is, but to come back to that, that's why active trading, you try to beat the benchmark, that try to beat the passive trading, because that's quite difficult in the long horizon. For instance, in the bullish markets, then if you do trade more, you definitely make more money because you're catching a lot more up moments. And but in the down times, then you actively trade more, then you lose more money, then you just hold your portfolio and do nothing. So there's a kind of waste of the funds in paying the exchanges for that. Yeah. So yeah, I think the ultimate let's say goal is you still want to active trade, but you want to outperform the benchmark. If you look at also like SP 500, so that's the US, the big index, it's quite hard to beat that index, to be honest. Yeah, on a longer term, of course. Yeah. I guess there's no any other questions. So yeah, will be our story, and I'm highly appreciate our partners within the work stream that's we put out all the work together, and especially for the PhD students. And thank you very much all to join our session, and we can be reached by LinkedIn, by different channels, and this video also going to be available in public, and feel free to reach us. Thanks a lot. See you.